Have you ever wondered how a tiny electrical signal can control high-power devices, from industrial machines to your car's electrical system? The secret lies in relays, small but powerful switches that act as the bridge between low-power signals and high-power circuits. Relays are everywhere, silently working behind the scenes to automate, protect, and enhance electrical systems. In today's video, we'll break down how they work, the different types you'll encounter, how to safeguard your circuits from voltage spikes, and why they are essential in automobiles. Let's jump right in. So, what exactly is a relay? At its core, it's an electrically controlled switch. Imagine it as a middleman between a low-power control signal, like a button press, and a high-power circuit, like a motor or a light. When a small electrical input hits the relay, it flips a switch, either mechanically or electronically, to connect or disconnect a separate, often beefier, circuit. This ability to use a tiny signal to manage something big is what makes relays so versatile. Now, let's talk about the most popular type, the electromechanical relay. This is the fundamental relay, and it's still everywhere because it's reliable, cost-effective, and can handle a wide range of voltages and currents. Here's how it works. Imagine a simple bar of iron, around which a coil of wire is tightly wrapped. This is the core of our electromagnetic relay. When electrical current is passed through this coil, the iron bar, acting as a core, significantly amplifies the magnetic field generated by the current. This intensified magnetic field then exerts a force on a nearby movable metal piece, the armature. Now, picture this armature as a lever hinged at one end and positioned close to the iron core. When a magnetic field is strong enough, it pulls the armature towards the core. Attached to this armature are electrical contacts, which are either opened or closed by its movement. When the armature moves, it changes the state of these contacts, effectively switching another electrical circuit. A stationary piece, the yoke, provide the magnetic path and a point of attraction for the armature. Once the electrical current in the coil is stopped, the magnetic field collapses and a spring, preloaded to counteract the magnetic force, pulls the armature back to its original position, resetting the contacts. In essence, the flow of current through the coil controls the movement of the armature, which in turn controls the switching of another circuit, all due to the magnetic force generated and concentrated by the iron core. Now, let's take a closer look at the contact points. They're the heart of the relay's switching action. There are two primary configurations, normally open and normally closed. Normally open relay is characterized by its resting state where the electrical contacts are open, preventing current flow. Energizing the relay's coil creates a magnetic field that pulls the contacts closed, completing the circuit and enabling current to pass. Thus, current flows only when the coil is energized, making the relay's switching action dependent on the presence of a control signal. Normally closed contacts are the opposite. Closed when off maintains a continuous electrical connection in its resting state. This means that when the relay's coil is de-energized or the field current is off, the electrical contacts remain closed, allowing current to flow through the circuit. These terms, normally open and normally closed, describe the relay's default state when the coil is de-energized. The contacts themselves are made of conductive metal, chosen for durability and resistance to arcing. When the contacts connect, the circuit is closed, allowing current to flow. When the contacts disconnect, the circuit becomes an open circuit. Now, relays come in all sorts of configurations, and they're named based on poles and throws. Single pole, single throw, or SPSD relay, characterized by its ability to control a single circuit with a single contact position, presents a fundamental on-off switching function. While the SPSD designation indicates the number of poles and throws, it leaves the default state of the contacts ambiguous, failing to specify whether they are normally open or normally closed. To address this ambiguity, the terms SPNO and SPNC are employed. SPNO denotes a relay with normally open contacts, where the circuit is completed upon energization, while SPNC signifies normally closed contacts, where the circuit is interrupted when energized. Including the coil terminals, The SBSD relay has a total of 4 terminals. The single-pole double-throw, or SBT relay, provides a versatile switching function, enabling a single circuit to be connected to one of 2 distinct paths. This is achieved through a common terminal that can be selectively connected to either a normally open or a normally closed terminal. The SBDT relay acts as a transfer switch, allowing for the switching between 2 separate loads or signal paths. This configuration requires 3 terminals for the switch circuit, along with 2 terminals for the coil, resulting in a total of 5 terminals. When you turn off a relay coil, the magnetic field collapses fast, inducing a huge voltage spike called back EMF or inductive kickback. This can fry transistors or microcontrollers driving the relay. Why? Transformer theory. The collapsing field acts like a mini generator. So how do we stop it? Enter the flywheel diode, aka freewheeling or flyback diode. Pop a reverse bias diode across the coil terminals. When the coil's on, the diode does nothing. When it's off, the back EMF forward biases the diode, letting the energy loop safely through the coil and diode instead of zapping your circuit. Problem solved. Relays play a crucial role in automobiles by acting as electrically operated switches that allow low power signals to control high power components. One of the most important applications is in the starter system, where the starter relay helps deliver battery power to the starter motor without overloading the ignition switch. Similarly, fuel pump relays ensure the fuel pump operates only when needed, preventing unnecessary battery drain. Headlight and fog light relays improve efficiency by reducing the electrical load on switches while maintaining bright and consistent lighting. Cooling fan relays activate the radiator fan when engine temperatures rise, helping prevent overheating. Power window and door lock relays enable smooth operation of high current motors with simple switch inputs. The horn relay ensures the horn receives full power without stressing the steering wheel switch. In air conditioning systems, a compressor relay controls the engagement of the compressor, optimizing cooling performance. Turn signals and hazard lights rely on a flasher relay to blink at a consistent rate, while windshield wiper relays allow for different speeds and intermittent operation. Additionally, anti-theft system relays are used in immobilizers and alarm systems to cut power to the starter or fuel pump when unauthorized access is detected. Overall, relays enhance the efficiency, safety, and reliability of a car's electrical system by managing high currents while protecting circuits and switches. And there you have it. Relays, from their mechanical magic to their contact tricks and that sneaky back EMF fix. These little guys are everywhere, quietly keeping our world running. If you enjoyed this deep dive, hit that like button and subscribe.